Hi, welcome back to i-NLP course. So in today's lecture, we'll be discussing about parameter efficient fine-tuning and quantization. In the last lecture, we had covered your large language models, LLMs, which are super large in terms of parameters, and they are becoming larger and more larger as the time goes by. So around 2018, the BERT and such models were in millions. So the parameters were in millions, hundreds of millions only. And when it came to 2019 or so, they started growing by manifold and reached to billions of parameters. And then we have models which are even have like 500 billion or even more parameters. So when the models are super large, and we had seen that if you want to update some information within the model parameters, so there are few options, and we had seen those options. So the straightforward option is doing fine tuning, which requires a supervised data set of a kind of considerable size. What else you can do? You can apply RAG and utilize the LLM and kind of infuse the additional auxiliary or newer information in context. Otherwise, there are other techniques like in context learning, few shot, and even zero shot. But you won't be able to add additional information in zero shot, but in few shot you might be adding some of the examples so that model learns the kind of expectation of what user wants the model to generate. So all of this we have seen. So today what I want to discuss, that even though the RAG kind of technique or method works pretty well, but it's not applicable to all the settings. So in some of the scenarios, we have to do fine tuning. And when we are doing fine tuning, we have a considerable a data set of considerable size, let's say 10,000, 20,000, 50,000 samples. And then what we want, given this very large model, let's say having 100 billion parameters, what we will do, we will do a forward pass for each of the sample. And let's say 50K is the sample size for my supervised data set for fine tuning for a particular underlying task. And then for this forward pass, you will have to compute 100 billion time, 100 billion computation will be performed. And then when you are doing backward, then you will have also need to kind of compute gradients, and you need to compute the gradients for all the weights and biases for all the layers of the transformers, and even the feed-forward neural net and so on. So it incurs lots of costs. So for doing 50K fine tuning, you will have to invest in the hardware. You will have to invest in terms of CPUs and GPUs and TPUs and so on. So is there a kind of is there a way out, or there is a technique to avoid this cost? And that's what we will be discussing today. So this is the topic of today's lecture. And we call this techniques, these family of techniques, I would say, parameter efficient training. So what do we mean by efficient is the topic of today's lecture. So one of the techniques, the first technique, it's called prefix tuning. Some people call it prefix coding. So what this technique entails, that in a normal setting, what you do, all of your, so what you do that, what these orange blocks are showing, that for each kind of task, let's say for translation and for summarization, for table to text kind of summarization, where you are given with a table and your model needs to generate a description for the table. Okay, and all the other translation and summarization is pretty much familiar to you guys. So what happens here, for this fine tuning, we have a kind of a specialized data set for translation, for summarization, and for table to text. And then what you need to do, as the previous figure you might have observed, that you'll have to do a forward pass for each sample, and then at the training time, and then you need to do backward pass and compute the gradients, the gradiental flow. So you will have to do this back propagation for each sample and for all the layers and so on. So what this method suggests, this prefix fine tuning suggests, or prefix tuning suggests, that rather than having these large language models, let's say here LLM having 1 billion parameters, so what you can do instead, you can freeze these weights. When I say freeze these weights, during the back propagation, you don't using the stochastic gradient descent or some sort of technique, maybe Adam and so on, you don't have to update these weights. So these weights won't be updated. Instead, what will happen, for each of your tasks, let's say task is table to text, so what you will do, you will say that, or maybe the task is summarization, so what you will say, that for each of your sample you will add a kind of a bunch of tokens, or they call it prefix, to it, and then you will feed the original document that you want to summarize, and this prefix will tell the model that what to do with this document. So essentially this is a summarization task. And why do we want to do fine tuning? So let me kind of go deeper a bit and tell you what is the intuition behind it. So given a pre-trained model, let's say this pre-trained model, and I will choose a different color, let's say, given this pre-trained model, which is trained on very large corpora, as we have already said multiple times. It's coming from some DB or some other sources these data set is coming from, and we pre-trained this large language model. So what this model has acquired, lots of word knowledge. So it can do many things, and it is super generic in a sense that it can do lots of things, but it's not kind of expert in one of the tasks. So maybe it is good at summarization also somewhat, and translation also somewhat, but it's not super efficient in summarization or maybe translation, or a particular kind of translation. So for these different tasks, what you want to do, you get a smaller data set, let's say D1 and D2. So you get very small data sets compared to smaller in comparison to the pre-trained corpus, very small, maybe just 2%, 3% of that, and even less. And what you do, but this data set is kind of having labels. So this was in pre-training stage, it was self-supervised learning. So we were kind of inferring or deducing the labels from the running text itself. But in this case, in these tasks, the data set will have the labels. So, and this is annotated by human beings. So that's why it's pretty costly to kind of create this kind of data set. But why do we want this? Because when we give a sample to this pre-trained model, that given this whole given this very large document, and I feed this to the model, and I want model to generate a summary. So let's say model generated something which could be gibberish, maybe model doesn't know what to do with it. Then we have the reference summary, or we can call it a gold summary, which is annotated by the human beings. So we have this annotated summary. So we'll take the difference, we will compute the loss, cross entropy loss between the reference summary and the generated summary. We pass this loss, we back propagate it. The weights of this LLM might change. So some of the weights, let's say, got changed, and then model next time it will learn that given these kind of documents, it needs to generate a similar summary. So model is learning the kind of nuances and cues and patterns from these samples, from the samples or fine tuning data set, even in the case of summarization or translation or for any task. So what model is learning? Model is learning what user wants me to do, and how it is learning by examples. What are those examples? Those are the samples from your fine tuning data set, right? So that's what model is doing. So similarly, what they said, rather than kind of changing these weights for the large language model, we can freeze these. So there is no gradient update is happening here. There is no change in the weights. What they instead did, they added a prefix to the prompt itself, or maybe the question, or maybe in terms of summarization with the original document itself, a prefix. And then when you do forward pass, it will be super similar. The forward pass will go through the LLM, and we'll depict this with a picture further. So it will be super similar. The forward pass will go very similar to what we normally do. But when we do the backward pass, so backward pass will go through only this prefix. So it will kind of train this prefix only. So this prefix will be learned, right? And you get the error also, you get the cross entropy loss. So these prefixes will be trained rather than training the model, right? So, and what effect it will give? It will kind of learn a representation, or it will learn a kind of representation which will kind of convey to the model that what model needs to do with it. And that's what model was learning from the fine tuning data set also. So this is the rough idea what the prefix tuning is all about. So as I told you, let's say given this example, and this example is ST-SB example, where you are given with two sentences and then model needs to find out whether they are semantically same or not. So let's say the example is on the scale of, and you add these kind of instructions so that model gets to know what it needs to do with these two sentences, right? So you will say when you are doing kind of a normal pre-training, normal fine tuning, what you need to do that on the scale of 1 to 5, how similar are the following two sentences, and then you will give the sentences, and let's say model predicted the score 3.8 pretty correctly. Then in case of prefix fine tuning, what it entails that we can remove this whole part and we can replace it with some sort of placeholders, or we can call it some representation or embeddings. You can call it some tokens, right? So you replace it with some token, and maybe these are randomly initialized, but not in the paper they propose, or they found out that it should not be randomly initialized. But let's assume that they are randomly initialized, and then you add these two sentences, and then let's say model, rather than predicting this 3.8 as a correct value, it produces 2, right? But the let's say real value was 3.8. So you will get the difference, you will compute the loss, it will back propagate, right? So when you are doing back propagation, these pre-trained weights won't change, they will not be changed, but the representation, this will be fine tuned, or the weights for these embeddings or representations will change. So how it will kind of help model to identify what to do with these sentences? So based on the laws, model and the representation or these embeddings or tokens will be fine tuned. So then they will change in such a way, the values of these will be changing such a way that model will learn that what to do with these two sentences 1 and 2, right? So what benefit we'll get from it? So it's parameter efficient. So we are not changing weights of the model, right? And prefix generation requires only 0.4% of the parameters required for fine tuning. So if you want to do fine tuning, how many dates you want to do, it's only 0.4% of the parameters that gets updated for this prefix tuning. And one additional detail which we missed, that these can be added to each layer. So at each layer you can add these prefixes. So this is at the input layer. It can also be added at the subsequent layers in transformers. So with the feed forward neural net, with the self attention and so on, right? What additionally it provides as a byproduct, that this prefix parameterization can be trained end to end, similar to a fine tuning. So very similar to fine tuning, end to end, but it is also private and friendly. So privacy friendly means that I don't want to give my, let's say, domain specific or very confidential data, and I don't want to fine tune with that kind of data. So what instead I will do, I will use this prefix training rather than giving the data to fine tune it, right? So you will be providing this prefix fine tuning, and then I don't want to show that what I want to do with this too. And it is just a corner case. Maybe for some of the applications, it's maybe not applicable for everyone, but for some sort of scenarios, it might be super interesting that given these two sentences, I might want to do something, and which I don't want to specify. Maybe I am calling a API rather than deploying the model. This model is not deployed currently within in-house in the company or in the organization. Maybe I am doing an API call and I am worried about what I am doing. Maybe it's something novel I am trying out, and it has some sort of commercial value. So I don't want to disclose what I'm trying out with this. So I'll be using this, and then based on the score, what I get, the loss I get, I will back propagate it, and then this will be learned, and this will kind of mimic and tell model what to do with it. Okay, so one some so from the paper itself, some of the interesting thing we have noticed, that in contrast to full fine tuning, prefix is also modular. So what do we mean by modular? That we train an upstream prefix which steers a unmodified LM, and therefore a single LM can support many tasks at once. So we can add different kind of prefixes, and with the same language model, same large language model, and then we can perform different kind of task, kind of complete different kind of task with the different kind of prefixes. So in that sense, it's pretty modular, right? And then one of the other interesting thing what we had seen, that we would have separate prefix for each user trained only that user's data, thereby avoiding data cross contamination. So what do we mean by that? Given a large language model, let's say user 1 wants to fine tune it for some task, and his requirement is like pretty specific. So let's say he fine tuned this this large language model with his own data set. So these are already fine tuned, and then user 2 also wants to fine tune for his data set. So when they are fine tuning their data set, the knowledge from this, and it's a normal fine tuning, so the weights of LLMs are getting changed. So when user 1 is doing fine tuning, the weights are getting changed. Maybe we can represent it with different color for better understanding. And when user 2 is doing fine tuning, some other weights or maybe some overlapping weights are getting changed. So what user 1 wanted, the original LLM and his changes, right? So let's say original LLM, let's represent it with so original LLM, the knowledge stored in original LLM plus the user one's changes, right? And then what the user 2 wants, that original LLM plus his changes, right? But instead what they are getting is, what they will get from this scenario, that they will get original LLM plus the changes by user 1, and then the changes done by user 2. So user 2 might get this kind of knowledge in terms of large language model. So this might be the final version of the LLM for the user 2, which was not intended. User 2 wanted only these two things, but this is additional because user 1 has used it already. So to kind of separate them out and kind of reduce the cross contamination, it is super good that prefix fine tuning, when they'll be using prefix fine tuning, they will have separate prefixes to kind of train, and there won't be any changes to the model. So they, even if there are 10 users, they'll have their own prefixes. So the original model is not getting changed, so they'll get the original content, original knowledge which is stored in LLM. So that's what the point I wanted to make here. So one of the other important information related to prefix fine tuning, so they said, if we go to previous slide, that these prefixes can be randomly initialized, but when they conducted some experiment, they found that rather than randomly initializing them, if you initialize them with the real word vectors, let's say, and this is random, and so they said, compared to random, if you kind of initialize them with any real word vector, so elephant or banana or beautiful, divide, and so on, what was the result? And then they said that if you know your task is summarization, so you can initialize them with the summarization or table to text itself, so it's even better, right? So that's what their conclusion at the end. Okay, so moving on, we will learn a very interesting technique called low rank adaptations, or LoRA. And the kind of objective is pretty similar to prefix tuning, but with a different kind of intuition and different kind of solution. So let's go about it. So what we have already discussed, that if we do full fine tuning, it is pretty slow, because you need to upgrade all the gradients, we need to update all the weights of the large language model, and it's pretty memory extensive. We'll see how much with exact figures with some examples, and then it's pretty expensive in terms of the resources and hardware that we are use, and in turn the cost, right? So, and this is what we need to do. So when we are doing back propagation, all the weights of the model needs to get changed. Okay, so what the LoRa or low rank adapters are, so rather than changing the weights of LLMs, they say that we can freeze the LLM, very similar to prefix fine tuning. We freeze the weights of the LLM, and what we can do, rather, we can have two metrics called A and B, which will kind of mimic the original matrix, which is W. So W is the pre-trained LLM weight matrix. And rather than updating W for backward pass, we'll be updating the, instead we'll be updating A and B, which are smaller metrics, and we'll see why does it make sense, why it is kind of mimicking, why it is possible to replace, or rather instead of updating the original W, we it is okay to update B, A and B matrix, and we'll getting the similar or maybe better results. So what happens in first step? So for each of, so during training, what you need to do, you need to do a forward pass, and you have a LLM pre-trained weight W, and then you have two smaller metrics A and B. So when you are feeding the input in the forward pass, it will also go through the whole W matrix and A and B matrix. And then when you are computing the loss and you are back propagating, then we don't touch the W. We will not update the weights of the W, but we will update the weights of only these metrics, A and B. And that's the trick, right? So let's move on to next slide and see what might be happening. So here you can see a pre-trained weight W, which could be Llama, which could be Gemini, or could be T5, Bard, BERT, whatever. And let's say this W has a shape 1024 cross 1024, so many parameters are there. And then what you can do, we can kind of have a kind of a mimic copy, or a kind of substitute for this W when you do back prop, that will be equal to these two metrics A and B, and these two metrics A and B can be of size 1024 cross 8 and 8 cross 1024, and where this 8 is kind of a rank of that matrix. And then if you kind of multiply these two matrices, you will get the same size as your pre-trained matrix. Okay, so in terms of A and B, how many parameters we are, so if we are doing the regular fine tuning, how many parameters we want to change, how many weights we need to update. So the number is 1024 cross 1024, 1024 square. But if we are using this setup, this adapter setup having matrix A and B, then you need to update how many weights, 1024 multiplied by 8 multiplied by 2. So it's just 1.5% of the original weight. So you don't have to update all the weights, you need to update just 1.5% of the weight, and you will getting very similar performance for your downstream task. And that's super phenomenal idea. So, and how are you kind of compressing the fine tunable parameters by either 0.5% or 10% of the total parameters in your LLM. So in your LLM, let's say 100 parameters are 1 billion, then only 0.5% of 1 billion or 10% of 1 billion parameters are updated, and you get very similar performance, which we'll see in the next subsequent slides. So let's see some of the observations also related to LoRA, that let's say your matrix is this, is have 5 values, 5 parameters, and they have 5 parameters, and this is your A and B, and if you multiply them, you will get 25 parameters to in the weight changes. So how many weight changes you had to do? You had to do only 10 weight changes, and at the end resultant matrix you get is 25, right? And this is called rank 1 matrix. If you increase to the rank 2, having like kind of 2 columns, and you multiply, you get even bigger matrix, and you have to train just 20 parameters, and but it will give effect of very bigger number. So moving on, what we had seen so far, just to conclude that, so in the forward pass the forward pass will go both to the original weight matrix that's coming from LLM, and then we will compute, let's say, loss, and when we back propagating the loss, it's going with this path rather than coming to that path, and we are updating this A and B matrix, right? Another thing which you need to remember, that this this LoRa adapters, these are called adapters, by the way. So these adapters, you just need you need to add that with each of the layer, or it's up to you. You can add at the lower layer only, or you can add all the layers. You can add to the feed forward layer, or you can also add to the multi-head attention, right? So it's up to you. But what they found out, if you add these adapters at each layer, that gives the kind of a best performance compared to all other variations where you add the adapters to the one layer, or maybe half of the layer, or maybe some of the feed forward only, or the self attention layer only. So now let's discuss some of the results. So you can see in this table, they had this Roberta model, and Roberta large specifically, and they fully fine tune it. So fully means they fine tune without the LoRa or other some sort of PEFT kind of technique. So it's kind of full fine tuning, and for all the tasks, you are already familiar with these tasks by now. So we have discussed in detail in previous slides, in previous lectures. So for each of these tasks, they found out that Roberta large compared to Roberta large with LoRa, which is like having minimal changes in the weights, either equal or it outperformed for all the tasks. So let's say a bit less here, but it outperformed in many of, or equal to in many of the tasks. And on an average, if we see, it outperformed the LoRa plane, which is not having LoRa. Similarly, for DeBerta model, they found the very similar effect where we get the overall average as better than the plain LoRa without plain DeBerta without LoRa, and with LoRa DeBerta outperformed the plain DeBerta. So it turns out that not only you are getting you are saving some of the computation and memory footprint, but we are also kind of saving and improving the efficiency, improving the performance of the model, right? So that's pretty shocking. On the other hand, if we see how many trainable parameters were there, so in Roberta large, there were 355 million parameters, and Roberta large with LoRa, you only update 0.8 million parameters. So it's pretty low, even not 1% of the original number of parameters, and you get better performance. So it's kind of shocking result what we get. And even in DeBerta, there are 1500 million parameters, and then you kind of in LoRa you just update 4.7 million parameters, and you get even better performance for this, right? So that's super interesting what we had noticed. So some more details and maybe more examples. So we discussed a bit about the ranks. So rank could be if you have just all the metrics, you have very large metrics and you have just one dimensional vector for it, the rank will be 1. If you add kind of more dimension to it, the rank will be 2, and so on. So if the rank is 1 for 7 billion parameter model, then you have to just fine tune, or you just need to update 167k parameters. And if it is 13 billion, it's just 220k parameters, and in case of 180 billion parameters, it's just 849k parameters. But if you increase the rank to, let's say, 8 or 16, you have just 1 million parameters to train with, and you get the performance of 7 billion model, and you just update 7 million parameters, and you get the performance of 180 billion parameter model. So in terms of percentage also, you can observe how much is the reduction in terms of a number of parameters. So for for 16%, only 0.04% of the parameters are getting updated for 7 billion model. So why this rank is important? Rank is important because if you are reducing the rank a bit, let's say we start doing rank 1, like A and B are both rank 1 metrics, so you might lose some performance. And so this rank kind of hyperparameter needs to be tuned, and they found out that there are some default values for that. You can try with that. So if we increase let's say the rank to 512 or maybe even more, so what you're doing, you are increasing the memory footprint, how much, and then you will have more parameters to train with, instead having a lower rank option where you have less parameters to train with, and the performance degradation is not that much. That's the crucial insight from this. So one fundamental question is, what we are doing, we are given a very large LLM with having 1 billion, let's say it's not even large, 1 billion like compared to today's model, but let's say we have 1 billion large language model having 1 billion parameter, and we need to update these 1 billion parameters to learn something. Instead, I'm saying we can learn only 50,000 or maybe more, maybe rather than 1 million itself, let's say. So rather than 50,000. So let's say I want to just update 1 million parameters. So you can see the difference, 1 billion parameters versus 1 million parameters. So you are just updating 1 million parameters, but you are getting effect of, or maybe performance of 1 billion parameter model. Why it could be the case? What is the magic behind it? So in the paper, they kind of figured it out, and they kind of hypothesized that these original LLM models, which are very large and they are trained with large corpus, but in a sense they are not optimized. So even if they have 100 billion parameters, they are not optimized, and they say interestingly that it has low intrinsic dimension. So they looks like a very high dimensional, but in a sense that it is very low intrinsic dimension. And what do they mean by this? That this can be further optimized, this matrix can be further optimized, and the rank of this matrix can be reduced. So let's say the rank of the matrix is super high, let's say the rank of the matrix is 1 million or so, but it can have rank of 20 or 50 and so on, or 60, 64 and so on, and even then you will match the performance of the model. So that's what the core kind of intuition behind the rank reduction of the matrix, and replacing the original pre-trained matrix with substitutes having lower ranks.